Well, let's see the next example. Right, two games are available. Right, the first game say, I bet $5 on number 7 in roulette. Probability of losing is 37 out of 38, and making 175 net gain is 1 out of 38. Right, the likelihood. And the second game is dice game called craps. Right, bet $5 on the pass line. Right, and you have likelihood of losing. You have likelihood of making the net gain. Then we see which one is good. Well, bet $5 on the number 7 in roulette. Probability of losing your $5 is 37 out of 38. And making a net gain of $175 has a likelihood of 1 out of 38 chance. Pretty much that's 38 different numbers on the roulette. Maybe at a different way, I don't know. I'm not familiar with gambling that much. But that's what it is. Or the second option, well, here is the example. I bet $5 on the roulette and whatever. I also bet same $5 on the pass line in the dice game. Right, the probability to lose your $5 will be 251 over 495, and you make a net gain of $5 to 44 over 495. Asking for which game is a better game, which means that which game you play you expect it to gain more, or if you're losing both of them, which one you expect it to lose less. Right, so we do the probability distribution. We get $5 lose and $175 win. Right, that is the chance. And when we put the value to be expected, we need to multiply the x with the probability. Right, 37 times 5 over 38. That's negative 185 over 38. And to win, that is $175 and likelihood is 1 over 38. That probability will be 175 over 38. Right, the expected value. We add them together, right? Negative 185 over 38 plus 175 over 38, that is a negative 10 over 38, which when we divide it, that is negative 0.26, right? That's the first game. And for our second game, that's that same $5. Losing is probability of 251 over 495. And the likelihood to win the $5 net gain will be 244 over 495. Right, so there are the values, and we're looking for the expected value. We'll do the same thing. I do the looking for the mean of the distribution. We have negative 1255 over 495 and 1220 over 495 as multiply. Then expected value here is negative 0.0707, right? So both of the game here we are losing money. For the long term of playing those games, the first game is expect to lose 26 cents, and the second game expect to lose 7 cents for each playing. That's in the long term, and therefore we can say if we play long term, right, we both expect to lose the game. The second one is better since that will lead to losing less. But the gaining, right, again, is coming with the risk. So the first one is with that much high risk of you losing money, then but if you play not that much long term, like many times before you losing that much, you gain the 175, then it will be cover everything you had lost in the beginning. But that's kind of also a good one. And the second one, you either win $5 or lose $5 in the short term, not that much. You may get balance already, right? Even for the long term, you just will lose 7 cents for each game you play. And the first one, for the long term, you will lose 26 cents for each game you play. Right? That is the balancing part, right? It's with risk, but gaining, of course, it's itself is with risk. Right, so but anyway, right? Gambling, either one, you're losing your money, right? The final winner will be the one, the owner of the casino, right? The owner. No one gambles actually wins at the end. That is because this, right? No matter what game they design, you are losing your money if you are the gambler, right? Not the owner. Right, let's see the next idea. Right, and make special wording, right? If we want to make a value is unusually high or unusually low, to judge. Like, for example, giving birth to 20 kids, right? Is having 17 boys over there is unusually high. Right? Is that unusually high? We will find a way, right? Try to see it unusually high or unusually low. We use the probability of getting it or other values that are more extreme, which means, well, to see if 17 boys out of 20 kids are unusually high, we use the probability of getting 17 or 18 or 19 or 20, or getting 17 or higher. If we want to see getting 2 boys are extremely low, right? Then we use the value of 2 boys, 1 boys, or 1 boy or no boy at all, as the probability adding together to see if it is unusually low. Right? More extreme means if you're looking for high, we go that value and higher. If we're looking for low, we go for that value or lower. The probability of them we're adding together, therefore we can see if that we get a value is usual or unusual. How we see unusual, right? If we still remember, we call that if we have a probability is smaller than 5%, then that is an unusual event. Or high or low doesn't matter. Right, so that is how we find unusually high or unusually low. So it's not a value itself, but the value itself or higher or lower, extreme depending on what they're asking. Right? If that's higher, unusually high, we'll go higher. If that's asking for unusually low, then we go that value and lower. Right? So let's see an example. Alright, the X is number of girls among 10 births. It could be 0, could be 1, could be 2, although it could be 10 girls all the way. Alright, so here is the table of number of X girls among 10 births. 0, that's 1%, 0.1%. To be 1 girl, that's 1%. Similarly, to have 9 girls, that's 1%, and 10 girls are 0.1%, and so on. Right, the likelihood of having 4 girls and of course the rest 6 are boys will be 0.25. We'll see how these numbers are coming from later, but well, now it is given as a probability distribution. Asking for is 8, and then usually high number of girls in 10 births. Well, it sounds very high, right? But let's see. So we're looking for 8 or higher, right? Because what I have seen before, If asking for extremely high, we go to that number and higher. So probability to be 8 or higher that means among 10 bursts, that's 8 or 9 or 10 are girls. Right? 8 girls, that's 0.044, 0.010, 0.001. Or you get 0.055 as the probability of getting 8 or more. Right here, the likelihood is greater than 5%. Which means it is usual, right? The likelihood is not smaller than 5%, it's more than 5% here, which means it is very usual to get, I mean, not very usual, but it is usual to get 8 girls in 10 births. It's usually high. Is 1 an unusually low number of girls in 10 births? Well, here asking for unusually low. So is 1 an unusually low number? Then we're looking for the probability of 1 or less, which is the probability of 1 or less, could be just 0. Right, 1% plus 0.1% is 0.011. Right, 0.011 is smaller than 5%, as we see, we have just seen, right? If probability is smaller than 5% or 0.05, we say it's unusual. If 5% or more, that's usual. So it is unusual. Low. The previous one, it is usually high. It is usually high. The 1 or less, 1 is unusually low. 1 girl is unusually low from 10 births. Right, so here is the thing. Right, we're looking for a certain value and extreme, more extreme, to figure out if that's usual or unusual. Or special probability distribution, or special discrete probability distribution. Now I have the first one is called Bernoulli. A Bernoulli probability distribution results from a Bernoulli experiment. Alright, the experiment only has, there's one trial. Just do your experiment once. Like flip your coin once, rolling your fair dice once. That Bernoulli is the person, right? So whichever the experiment referred to is just have two categories, right? That's only one trial, and there are only two outcomes. To be head or tail for the coin flipping, to have a value of success or fail, like the example before, we have the roulette. If we have the value of 7, that's success. If we have other values, that's fail. Right, to be true or false also could be the outcomes. Right, but that's only two outcomes. So that is Bernoulli experiment, and the probability distribution is called Bernoulli probability distribution. When tossing a fair coin, the random variable is defined as 1 if coming out is a head, is equals 0 if coming out is a tail. Then the experiment here corresponding to the random variable is one outcome, one trial, two outcomes. Right, one outcome, one trial to be the experiment, right? To flip a coin, that's only one trial. And two outcomes, it could be either land on head or land on tail. Right? 1 is head, 0 is tail, then the coin is fair. By tossing a fair coin, a fair die, to win if it lands on 6. Right, so it is also, we have a random variable have 1 if wins, 0 if lose. Could be defined that way. Then we have the probability distribution. That wins if it lands on 6. So we have 1 out of 6 ways to win, and the other 5 number are the losing part. Right? So 1 or 0 defined that way. It could be defined in different ways, of course. That is the Bernoulli probability distribution, which we have one experiment or one trial of the experiment and 2 outcomes, either success or failure, right? Either win or lose or something else. Right, that is the Bernoulli probability distribution. Then we have something called binomial probability distribution. Is getting results from n trials Bernoulli experiment. So we had like a Bernoulli experiment of tossing a fair coin. Instead of 1 sphere, we have n times. Right, like before, giving a birth of kids to have either boy or girl. If have 1 kid is a Bernoulli experiment. But when we have 10 kids or 20 kids of newborn, that is binomial distribution. That's 20 trials or 10 trials of Bernoulli experiments. We have 1, 2, 3, 4, n different trials. Each trial in a success with probability p. Right, so there are n independent trials. The n trials are independent to each other, which means the first one success doesn't affect our second one being success. Right, then success with probability of p, and the fail with probability of 1 minus p. Like if you play you flip the coin, you have landing on the head is success, landing on the tail is failure. Right? Then if the coin is fair, you have the probability of landing on head will be 0.5, and the landing on tail is also 0.5. We're asking for what is the probability of getting exactly k success. Right, so that is the step-by-step building of these distribution. Get to know the Bernoulli before, then here is the now more than one trial, it's n trials, but n independent trials. Right, each trial has a success of p, and I have a fail with probability 1 minus p. Right, so what is the probability of getting k success? K successes is the question here. Right, so let's denote right, the EI such that event I's trial is success, which means E1 is first trial is success, E2 is second trial is success, and so on. Alright, then the first case successes will be the probability that the first one is success, second is success all the way to the case is success, and from k plus 1 a failure, all the way to the end a failure. Right, that makes sense, right? The first is success, second all the way to the case is success, and the remaining n minus case of failure, which when they say independent trials, that intersection is the product. Right, the first case success, and the remaining n minus case are failure. Which we get k success and minus k failure with probability of p and the 1 minus p. So if p to the k times 1 minus p to the n minus k is the probability of success and failure. We want the probability of k success. Right, then we figure out the probability of first k success is p to the k times 1 minus p to the n minus k. Right, but we have n different trials. That one is the special case that's the first k of success. But we have n different trials. And the k item need to be selected. Right, so the way we selection is and choose k. Ways to be happen, right, of k different successes. Therefore, the probability of x equal k is same probability repeating that n time nck times. That is k successes among n independent trials, which is so-called the binomial distribution, and that is the formula, depending on n, depending on the k.